Before we talk about DC circuits, that's direct current circuits, and we get into actually solving problems with them, we just need to go over the basic parts of a circuit. So different parts here. This is the symbol for a battery or some sort of EMF source. EMF stands for electromotive force. So an EMF source would be something that pushes electrons, electromotive, that pushes electrons force around wires or pushes them through a circuit, aka a battery. It provides a voltage. So your battery, sometimes you'll see a little script E for that, will be rated in terms of electrical potential difference, aka voltage. Like these two batteries are 1.5 volts. That's a common voltage for almost all batteries there. These little squiggly lines are resistors. We use these little squigglies to represent resistors. Sometimes you'll see a box with maybe a squiggly inside of it or something along those lines. Whenever they're placed very close to a battery, often those are internal resistors. Sometimes you'll see a box around the EMF source and the resistor to indicate that is an internal resistor. An internal resistor would be the resistance of the battery itself, because all batteries actually, at least to a certain extent, fight against itself. There is resistance inside of the battery preventing the ideal chemical reaction from taking place. Now this here is an ammeter. It measures how much current is flowing through a wire, like how much current is going through this wire in particular is what this ammeter would measure in number of amps. That's the unit for current there. Filament lamps look like this. They can either have a circle with an X in them, or maybe they try to show you the filament a little bit better with kind of a loop inside, sort of a script L looking thing. Generally, though, it's connected to the sides. I apologize, mine is not there. Where wires intersect, those are called nodes. At nodes like this, and you'll see sometimes an open circle to indicate a connection with a node, but where wires intersect, current has a choice. It can either come this way around or it could go that way around. Okay, so the current will divide at nodes and then recombine over here. This is the symbol for a capacitor, two parallel plates there. Capacitors, they build up charge and then they will discharge that charge that's built up very rapidly. Most common, easy example to understand would be a car's blinker, right? A car's blinker, the capacitor inside charges for a little while. That's when the light is off, and then it discharges rapidly, giving you a very bright flash of the blinking bulb, right? The little light bulb that is the blinker inside of a car, and then turns off as the capacitor starts to charge up again. This is a voltmeter. It measures the electrical potential difference or the voltage drop or the voltage across something. Notice this is in parallel. Think two parallel lines, capacitor, voltmeter. So the voltmeter is telling me the voltage, V, the voltage of this capacitor placed in parallel, ammeter in series. Notice it's in the line. I really should have broken the wire up there. Now wires we will consider to have zero resistance, meaning how much it fights the current coming through, how much it resists the flow of electrons through there. Resistors, on the other hand, generally have a known R measured in ohms. We'll talk about that in the next video. And those are going to resist the flow of electricity. Now, resistors come in many different ways, shapes, and forms. In the lab, we're going to use specific carbon resistors that have a very good constant resistance under certain power requirements that work perfect in the lab. But a resistor is anything that resists the flow of electricity. A heater is a large resistor. It's a bunch of wires inside of a heater, and you put electricity through it, and the wires heat up. A light bulb technically is a resistor, although it doesn't follow Ohm's law. We'll talk about that perfectly. But anything that resists the flow of electricity can be considered a resistor. Now, the equation for current up here, current I equals delta Q, or the amount of charge that passes by, divided by time. So charge divided by time. And like I said, the unit for current is amps, right, or amperes. But short, a little bit of physics slang, if you will, amps there would be the unit for current. Charge per, how much charge passes by a given point per unit time. Now we know that what charge actually flows is the electron. The electrons are on the outside of the atom. They have a negative charge and they flow around the wires. Now I should point out, in a circuit you must have a closed circuit. If anything is broken open, for example, if the wire was cut right here, no current would flow through this loop over here, okay, because there's an open circuit there. Likewise, you can actually short out an entire circuit or just parts of a circuit. For example, if I drew a wire around this filament lamp right here, or some piece of metal was connected across the filament lamp, current, or electrons that are flowing, right, charge per unit time, electrons that are flowing, current, always takes the path of least resistance. I mean, we all do. That's life. You take the path of least resistance if you have a choice. So in this situation, all of the electrons coming down this line will go around that filament lamp. Skip it altogether, thus this filament lamp would not light. Now, this isn't that big of a deal here, except your lamp wouldn't turn on because you have other resistors. On the other hand, a much bigger deal comes if you have a connection, let's say a wire that runs here, right? If you have a connection with just wires, this sort of situation could be a problem because the current would come out of the battery and then takes the path of least resistance. It technically would divide, but this path has a straight wire in it next to no resistance. So it's going to, for the most part, skip this lane, come over here, skip going that way, and just come down the wire, very low resistance, and then check it out, it only has one resistor to go through for a circuit that was probably designed to have many, many things that resist electricity on that. If this resistor wasn't here, we'd be in big trouble. At that point in time, because there's nothing to slow the current down, so to speak, no resistor to fight it, the current would skyrocket. Would grow, in mathematical senses up towards infinity. In reality, it can't get that far. You have an internal resistance in your EMF source that would eventually stop it. But whenever you have that much current going through your wires, now your wires actually get really hot. They begin to act like resistors. Your wires get really hot, and that's what causes house fires with a short circuit. Now, current actually flows what seems like an odd direction. Current flows as if it is as if positive charges were moving. We know it's the negative charges, we know it's the electrons that move, but for historical reasons, we consider current flowing in the positive charge direction, out of the long end of the battery in a schematic. Okay, so our current would flow like this. We'll call the current here I, and whenever it gets to a node, it would divide. I1, well, let's call that I2 over there, and let's call this I1 in that lane. So it's going to split up. I is going to split, the current in that coming out of the battery will split into I1 and I2. It's an intersection. Some go straight, some take a right. In this case, comes around here. This is still I2 coming around. Here's I1 coming down. And then they will remerge once again at that next intersection into your total current I, continuing to flow around like that. So current flows the positive direction as if it was all positive charges doing the moving, which is somewhat peculiar. Long story short, you just need to remember that current comes out of the long end of the battery, right? Comes out of the long and goes around to the short. Now here is what resistors you will use in the lab look like. They are carbon resistors, and they are marked color-coded according to this key down here, to tell you what resistance it has. The unit for resistance is the ohm. There's the Greek letter ohm right there. And it has multipliers and bands on there to tell you what it's worth. So for example, this one over here is coming from this first digit, a 1, the next two digits, zeros, so 100. Multiplier is times 1. So this is just a 100 ohm. There's the actual answer. 100 ohm resistor here. Tolerance tells you how much we could fluctuate that. You'll need that for the lab coming up tomorrow. All right, so take a second, quickly sketch this down, or look it up on the internet and print it off either way, and then I guess I'll see you in class tomorrow.